This is number 3 of the mock. This is some organic-y stuff, and then another one we have to get ideal answers from. Okay, this is number 3. Where's my pen gone? Number 3. Don't know where the pen's gone. All right, we've got to compare butanoic acid, ethanol, ethanoic acid, and water. And we've got to give the most acidic to the least acidic. Now, there's 2 answers here, aren't there? Let's do the most acidic here. This is ethanoic acid is going to be the answer. Okay. And number 2 is going to be, what is it? Butanoic acid. Butanoic acid is going to be the second most acidic. Third one is going to be water. Okay. Where's water? There's water. And the last one, oh gosh, can we squeeze it in? Is going to be ethanol. All right. So this is ethanol. And we've got to explain why. Okay, there's ethanol. All right. Now, there's obviously 2 ways of looking at this. Before I go on, though, let me put these in because it's annoying me. So the most acidic is going to be ethanoic acid, ethanoic acid. Then we have butanoic acid, and then we've got water, and then we've got the least acidic is ethanol. Okay. All right, and all of these are going to be in some sort of equilibrium with their conjugate. Okay, and let's try and explain why they're in this order. Okay, there we are. Oh, that's pretty ugly. All right, so let's draw this. Now, as you all know, there's 2 ways to answer this, and you all do, well, the vast majority of you do it in a different way than I would do it, I must admit, but that's fine. Your answers are fine. Okay, you do the stability of the carbocation. But I don't tend to do it that way around. But there's nothing wrong with it. This is water plus H. Whoops, this plus H plus, and this is plus H plus, and this one is ethanol, the ethoxide ion. There's the ethoxide ion plus hydrogen. Oof. Now, how would I do it? You don't have to do my way at all. This is my answer. Well, what we're doing is we're weakening this bond. Okay, so this is an electronegative group here. Okay, it pulls electron density away from that bond, facilitating the release of the proton. Okay, so next to this we have a methyl group. This guy. This has a positive inductive effect. Yeah, and it pushes electron density onto the bonds and strengthening the bonds. Okay, and that's to be weighed up against the COO part of the molecule, which is taking electron density away. But one way or the other, this kind of wins. The electronegative part weakens the bond, facilitating the release of the proton. Now, next one down, same thing. The strength of this bond is what it's all about. But in this case, it's next to a highly inductive with a positive inductive effect. This is also a positive inductive effect. This guy pushes more electron density on, strengthening this. So between ethanoic acid and butanoic acid, ethanoic acid is going to be the stronger because this bond is weaker, because the propyl group in this case pushes electron density onto the OH bond, strengthening it. All right, now the water, well, this is going to be, it's not a C double bond though, it's just an oxygen. So this bond will be weakened by the electronegativity of the oxygen. Now this one is a similar case to water, but instead of a hydrogen, you've got this ethyl group pushing electron density onto this, strengthening this bond. So that would be my answer. As you go down here, the OH bond is strengthened by the, oh, my pen's gone weird. It's strengthened by the inductive effect. All right, the positive inductive effect. Okay, that's my answer. Your answer is just as good, and I have no problem with it. Your answer talks about the carbocation. So in this case, this one is stabilized. Okay, it's next to this methyl group, and this takes electron density away, and this pushes, but not too much. So relatively speaking, the charge, the negative charge, is sort of distributed over the molecule. Here, because you have and therefore the proton is less likely to jump on because the negative charge is distributed over the molecule. So we say the cation here is stabilized. Okay. This one, well, not quite the same. Okay, it is spread over the molecule, but it's pushed back to this side. So the O minus here is more likely to grab the proton. This one, there's not much stabilization here at all, so this will go back relatively easily. And this one, well, you're pushing electron density onto the O, so this carbocation, this guy here, is very unstable, and it will reabsorb the proton to go back to the ethanol, so making it a weaker acid. Interestingly, this guy is a very, very, very weak acid, as we know, but this guy is a very strong base. Okay, because it really wants protons, doesn't it? So the ethoxyline is a very strong base. So that's what the kind of answer I wanted here. Okay, now how do you put all that down? Well, you've just got to condense it into 5 or 6 lines. Now, I'm not going to do my version here because you all seem to prefer the stability of the carbocation. Okay, which is absolutely fine. Okay, all right. So whatever method you prefer, my method is fine. Your method is fine. Okay, but sort out a perfect answer for this type of question because these will come up. All right. Let me stop the video and do the next bits. Oops, I don't know where I am now. So 1 second, my computer's gone weird. All right, let me stop. Okay, now this one's a weird one because it's one of those nooks and crannies of the syllabus, but you must know this. Methanoic acid is very easily oxidized. Ethane dioic acid is very easily oxidized as well, but not as easily as this guy. But butane dioic acid isn't oxidized. Okay, so what would give a positive test for this guy but not for this guy? This guy's never going to give a positive test. Okay, so we can ignore this. All of this is not going to be oxidized. But these two are. All right. So we need a very gentle oxidizing agent. And the one I think we talked about in class was Tollens. Okay, and we're going to get a silver mirror if we use Tollens because it's oxidized. You can also use Phalins. Okay, Phalins. Okay, and if you use Phalins, you get a brick red precipitate. Okay, now we're going to oxidize them both. This isn't going to oxidize at all, don't worry about it. So we can oxidize this, excuse me, with potassium manganate. It's got to be acidified and there has to be heat. Okay, and it's aqueous. All right, and what are you going to see there? Well, it's going to go from purple to colorless. Okay, now some of you said effervescence. Yeah, you should see effervescence because it gets oxidized to carbon dioxide, doesn't it? Effervescence. All right, which is no problem, but definitely you should mention the color change first. Okay, let me stop and find the next bit. Okay, this one asks about some NMR. You've got the same compounds, I think they're the same as we've just had, and we've got to complete the table. So let's do the harder one first. Number of protons. This is hydrogen NMR, and this is carbon 13 NMR. Okay, so this hydrogen is different from this hydrogen, so we're going to get 2 peaks there. This is a symmetrical molecule, so this hydrogen is the same as this hydrogen, so you're going to get 1 peak, and this hydrogen and this hydrogen are the same, and this hydrogen and this hydrogen are the same, but they're not the same as each other. So this and this are the same, and this and this. So you get 2 peaks. Now let's do the easier one. I hope it's easier. Let's get rid of that. Let's do the carbon. All right, there's only one type of carbon there, so you're going to get 1. There's only one type of carbon here. They're the same, so you're going to get 1. Now here, it's symmetrical, so this one and this one are the same, and this one and this one are the same, so you're going to get 2 carbons there. The spectrum of this guy is done with heavy water, D2O. Okay, describe and explain the difference observed between this spectrum and the proton NMR with that. Now, obviously, the big difference is the peak responsible for this proton. okay, will disappear. Okay. Oh, it doesn't look like I've spelt disappear right there. Is it one S, isn't it? So let's get rid of that. And let's say that. The OH peak will disappear, this one. This one won't, this will stay there, but the OH peak will disappear. Why will it disappear? Well, because this proton is labile. Now, there's nothing wrong with that, but I also would like you to say it exchanges with the D2O. Okay, so some of you said this, you get OH plus D2O, and you get OD plus DHO. That's a nice way of saying it. This is proton exchange. Okay, hope that one's okay. Let me stop this. Okay, now we've got some mechanisms here. One for dibromobutane is used in the synthesis of the dicarboxylic acid J, and the diamine K is shown. There you go. So obviously, how are we going to go to get to the carboxylic acid? We're going to replace these with OHs, aren't we? So we're going to get an OH there, CH2, 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 OH. And now we've got this on there now, and we've got 1, 2, 3, 4, 5, 6 carbons, and we've only got 4 carbons here. So somehow you've got to go through, you've got to put this on, haven't you, to increase the chain length. All right, so we're going to have CN there. We're going to have our CH2, 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 and our CN there. Now, this is obviously from here to here is an oxidation, and from here to here is a reduction, isn't it? All right, and we'll see how we do those in a minute, I guess. Let me stop the vid. Okay, these are the conditions and the reagents. Let's have a look. Now, you can't get these wrong. All right, so step one, how do we do that? Step one, let me get a nice blue pen. We use sodium hydroxide, aqueous, that's important, and heats. You've got to say the heats. Number two, step two, it's an oxidation, so we use the purple stuff, potassium manganate, aqueous, and it's got to be acidified, and heat again. Now you could have also used the potassium dichromate there, again aqueous, again acidified, again plus heat. You've got to say the heat. All right, lots of you didn't. How do we do step three? Step three, we use KCN. Okay, we use an aqueous ethanolic solution, so aqueous solution, and we heat this as well, don't we? All right, that's replacing a bromine for a CN. Okay, we can't use HCN. HCN is only used on aldehydes and ketones. And the fourth one, how are we going to reduce? We're going to use our friend here, lithium aluminium hydride. And if you like the conditions, we use dry ether for this. Okay, or we can also use hydrogen in nickel. All right, nickel catalyst and heat again. Anything else? There's another one they can use. It's sodium in ethanol. Pick your favorite your favorite reducing agent. I would stick to this. Okay, that's the one in the syllabus for this reaction, and this is the reaction between a nitrile and an amine. I'd pick that one. All right, let me go to the next one. We're zooming through this one. Okay, this is the last question. Polyamide L can be synthesized from that, J and K. Draw the repeat unit. Okay, now these are trickier than they look actually. Now what we're going to have, we've got a dicarboxylic acid, so we've got CH2 twice, CO. I'm looking at this side, and this side I've got CO. Okay, that's that. All right, and I'm going to add it to this. So I'm going to get NH. You've got to show this group fully displayed. Okay, this isn't displayed. This is displayed. Okay, you've got to show the group fully displayed, the amide group. Okay, let's continue. Where are we? This goes on to give us CH2 6 times, And then we have NH, and there we are. But is this the repeat unit? I think it is actually. Now, if you can imagine cutting this and pasting it here, copying this, and putting it there, it would generate the molecule, wouldn't it? So you've got to be so careful where you cut this off, but this is one repeat unit. Anyway, that's 18 marks. Let me post this now.